Hi, welcome back to lecture 25 of MA 221. Today, our topic will be parametric curves. Okay, so how to define curves using parametric equation, that is the main concern. But before that, the question is how the curves in XY plane look like. So there are two ways you can define a curve in XY plane. One is might be y is equal to fx. This is one standard form, and the other is when you define something like x equal to g of y. Okay. For example, you can think of like a circle, equation of a circle, which is say something like this. Um, so say this is the equation of the circle, x minus 2 square plus y minus 3 square, same as 1. Okay. So this equation is called implicit equation, where you cannot like separate y or x like this. Okay. Not by at least simple formula. Okay, the next thing is, what is a parametric curve? So a parametric curve in xy plane is the set of points xy, so all the pairs satisfying parametric equations, which are like x equal to ft and y equal to gt. Okay. And basically you have a like restriction on t as well. For example, ft comma gt, this ordered pair could represent the position of a particle at time t. Okay, so for parametric equation, we basically try to define the motion of a particle or something of that physical existence to how the particle sort of moves when time t varies. Let us see one example to um, visualize that maybe. Okay, so the example is sketch the graph of x equal to 1 plus t and y is equal to t square minus 1, and t is in between -1 to 4. So how to sketch this graph? So this is a standard parametric equation. Okay, most of the time parametric equation look like that only. Okay, so my job is to draw the graph. For that, I have taken these points. So t varies from -1 to 4. So if you look at this column of t, I have taken -1 and then minus 0.5 and then 0. So basically at each step, I'm adding 0.5. Okay. So I'll get 1, 1.5 and so on, all of these points. So I get this number of points there. And I'll evaluate what is the corresponding value of x and y when my t is -1. So if my t is -1, I'll get x to be 0 from this and y to be 0 as well. Okay, from the other equation of y. And similarly, if I try to evaluate all the values of x and y, changing the value of t, I'll get this table. Okay, let me just write it down. Okay, so this is the complete table. And then I basically draw all of these points. So 0, 0 is the first point. The second point is like 0.5 and -1.5, 1.75. So something like this. If I draw all of these points, I'll get something like this as my graph. Okay. So this point will be at t equal to 4. This 0, 0 at the origin point will be when my time is -1. Okay. And when t is equal to 0, I'll get the like lowest point of the graph. Okay. So more or less the graph will look like this. Now, this graph is kind of similar to us, but to see the full picture, what we need to do is to convert this parametric equation into our very known equation involving x and y. Okay. So for that, what we need to do is we need to eliminate t and convert the parametric equation into Cartesian equation in x and y. Okay. But how do we do that? I know that x is 1 plus t given in the problem and y is t square minus 1. So from this, I'll get the value of t in terms of x, right? And I'll put the value of t in this second equation. So y will be same as x minus 1 square minus 1. So this is nothing but y plus 1 is same as x minus 1 square. If you remember a little bit of um, the geometry, then you might recall that this is an equation of a parabola. Okay, the vertex will be 1, -1. Okay, but in fact, the graph will be a piece of a parabola between 0, 0 and 5, 15. Okay, because when we talk about parabola, then it should be like, going to infinity, right? It should like go on and on and on. But for this parametric equation, the graph should be like restricted from like origin to this point, right? That's what I have written, that it'll be a piece of parabola from 0, 0 to 5, 15. 0, 0 is due to t is equal to -1, and this is due to t equal to 4. But sometimes in physics, why parametric equation is more important is, so this equation basically says that, say a particle was at -1 time, the particle was at the origin. And then when the time increases, it basically follows this path and then this path, and at t equal to 4, when time is say 4 minutes or something, the particle reaches here. So that is how, when you do like physical applications and stuff, this parametric equation things are become useful. Okay, next example. You have to sketch the curve x equal to 2 sine t and y is equal to sine t, where t is in between 0 to pi. So for that, I have taken just 0, pi over 2 and pi, these 3 points as my value of t, and from that I'll try to guess how the graph will look like. So at 0, if you again use these two equations, x is equal to 2 sine t and y is equal to sine t, I'll get at t equal to 0, x will be 0 and y will be 0. At t equal to pi by 2, x will be 2 and y will be 1. And at pi, it will be 0 and 0 again. So if I try to draw it, so at t equal to 0, I'll be at origin, right? At t equal to pi also, I'll be origin. And when my t is pi over 2, I'll be at 2, 1. So this is 2 and this is 1, something like this. So that means from time 0 to pi over 2, the particle moves in this direction. And for the other half, pi over 2 to pi over 2, pi over 2 to pi, the particle will return back to the origin. Okay. So that's why parametric equations are like very nice. Because if I convert this to um, the Cartesian coordinate, then, or Cartesian equation, I'll get something like this: x equal to 2 sine t, y, and So basically this means sine t is x over 2, right? And again, y is equal to sine t implies y will be x over 2, right? So this graph is same as y equal to x over 2. But if you use some graphing calculator or something to draw, the graph of y equal to x over 2, you'll get only this. Okay, there is no question about direction. Okay, so you should notice the difference. If I use the xy system, then I'll get only a line. I don't know how which direction the particle is moving or something like that. There is no information. But if we use the Cartesian coordinate, if we use the parametric equation, then we sort of have an idea that the particle sort of moves in like a different way. For this time interval, the particle is going up, and then for the other interval, it's going down, something like that. Okay, I hope things are a little bit clearer to you. Okay, now the next example. So in this example, it is being said that a particle travels clockwise twice around a circle of radius 2 centered at 5, 3. So that means the in Cartesian coordinate in xy equation, the circle will be like this. This will be the formula for the circle, right? Because 5 and 3 are the center of the circle and the radius is 2. Okay, so therefore this is the equation of the circle. But what more is being said is the object starts at 5, 5. So I have to find a parametric equation for the curve. Okay, so let us first try to draw it. Okay, cool. So say this is the center and this is the circle, say, right? So this is the radius 2. This will be also radius 2. But then this, and also let that this is theta. Then using the plane trigonometry, you'll get this length to be 2 sine theta. And this length to be, let me use something else. And this length will be 2 cosine theta. Okay. Okay. So, and the particle starts at 5, 5. That means, it starts around like here, right? And it goes like this one time through the circular path and then twice around the circle. So therefore, one more time it just moves and comes back to the original point. Okay, so how to get the parametric equation for this? So x will be 5 plus 2 sine theta. How I get that? Because so say the particle is here. Okay, so this is the point where the particle is right now. Then I'll get, then what is the distance? So how I can get that point back? Okay, now what is this distance? This distance will be, you know, so what is this distance? This will be 3, right? Plus 2 cosine theta, right? Again, how I get that? Because I know that this distance is 3, right? This distance is same as this distance and this is 3. And I also know that actually they should be like passing through this. Yeah, I'm pretty bad at drawing. So this distance is 3 and this part is same as this part, which is 2 cosine theta. So the whole distance will be 3 plus 2 cosine theta. So I'll get y to be 3 plus 2 cosine theta. And similarly, for the x distance, so from here to here, for this distance, it will be 5 plus 2 sine theta by the same logic. Okay. You should try to think about it and get the result. Okay. Okay, now let me clear the picture a little bit. So y is 3 plus 2 cosine theta. And now theta should be in between 0 to 4 pi. Why 4 pi? So the particle starts from here. It goes one time through the circle. So I'll traverse 2 pi distance, and then it goes along with the circle second time. So therefore in total I'll be like moving 4 pi angular path. So that's why my theta is varying from 0 to 4 pi. This is because two circular portion. Okay, now, so this is the Cartesian, this is the parametric equation. And now if I try to get back the xy equation from this, how will I proceed? Same way, I'll evaluate sine theta in terms of x. And then again, from this, I'll evaluate cosine theta in terms of y. And then I know the famous trigonometric identity, which is sine squared theta plus cosine squared theta is 1. And then I'll put all of this inside this equation. And then I'll just try to simplify a little bit to get my original equation, which was this. Okay. Okay, cool. For the next example, again, I am given with a parametric equation, and we have to draw the graph. Okay. So first, let us try to get the xy equation out of this parametric equation. So again, I'll get cosine t to be this, and sine t to be in terms of y, and then use the identity again. Sine squared theta plus cosine squared theta is 1, that identity, to get back this equation. And again, by plain trigonometry, you might remember this is nothing but equation of an ellipse. Okay. So to draw the ellipse, we sort of from this only we sort of can draw this graph, but to get how the particle moves, which direction and stuff like that, we need to consider the parametric equation as well. So at 0, so remember t is varying from 0 to pi. So I'll take this 3 values of t to guess how the graph will look like. So at 0, my x and y will be 8 minus 2. At pi over 2, it will be 3, 0. And at pi, it will be minus 1, minus 2. So if I draw that, if I draw the ellipse from this xy equation and also use this parametric information that I have, then I'll get that at pi over 2, the particle will be here. At pi, it will be here, and 0 will be here. So therefore, it will sort of move from this to this direction and this direction one time. Okay, cool. For the next example, what I'm going to do is, again, the same sort of problem. I have a parametric equation in terms of x and y, and t is the independent variable, and t varies from 0 to 2 pi. So this graph is not very easy to draw. You have to consider many things, but if you use Wolfram Alpha, which is pretty famous software to draw all kind of graphs, you will see that this is the complicated looking graph. So using parametric equation, you can get a lot of sort of strange graphs as well. Okay, cool. For the next example, it is asking that find a parametric equation for a centroid. Okay, what is a centroid? So let me draw a picture to better explain. Say I have a circle, or say a wheel, and the wheel there's a point marked already on the wheel. So this is the point, and I'm sort of focusing on this point. So when the wheel sort of moves, this red dot or my chosen point also moves, right, along with it. So I'm basically tracing this point again and again. Okay. So if I only focus on the point, and then if I draw a line through all of this different position of this point, I'll get a curve, right? And this red line is called a centroid. Okay. Say A is the radius of the wheel. Okay. So when I focus on one, say this circle, then again I'll try to consider the theta as the central angle like this, and then I'll get this length to be a sine theta, and this length will be a theta. Okay, this is not very hard to see, but yeah, because this length and this length is a, right? And we are moving theta. The angle is theta, so therefore this length, the circular length, will be a theta. Okay, and this line will be a sine theta, which is very easy to see, okay, by using trigonometric identities. And this length will be a cosine theta. Okay, so therefore when the particle is like here, okay, if the particle is here, then what is the x and y coordinate? X will be, so x will be just a theta minus a sine theta, right? Because this length is a sine theta, and okay, so the issue is that this formula, I'm writing it just to complete it. The parametric equation are given by these two formulas, where theta is in between 0 to 2 pi. But how we get that is not very easy to visualize. So there will be like two circles coming into picture, and getting the equation of cycloid will not be easy. So I'll not draw the picture here, but I might be mentioning a link of another video where you can like visualize how we get that equation of cycloid. But yeah, I'm skipping this portion for now. Just remember the formula for the parametric equation formula for the cycloid will be this. Okay. How I get that will be attached. Okay, cool. The next thing will be how to do calculus on parametric curves. Say C is a curve defined parametrically. Then can we talk about the slope of the curve? Say P is a point on this curve C. Then what is the tangent at this point, and all sort of calculus question, how to deal with those. So yeah, how to find the slope of the tangent at P, and then next question would be where the tangent is horizontal or vertical, and all this sort of uh, standard question will be coming up. So by the chain rule, dy dt will be dy dx and then dx dt, right? And by cross multiplying, I can get the standard formula that will be very useful to do any calculus here for the parametric curve. So this is an important formula that we need to know. And these are the three scenarios. If my dy dt is 0 and dx dt is non-zero, then we'll have horizontal tangent. If my dx dt is 0 but dy dt is non-zero, I'll have vertical tangent. And if I have both of the derivatives at t to be 0 for the parametric curve, I can only say that the curve may have a sharp corner or cusp at the point. Okay. And all those points where both of the derivatives vanish, those are called singularities. And what does it mean? In simple words, this means a point where differentiability is a concern. Or differentiability is lacking. Okay. Now the next question would be, can you say anything about concavity or convexity? So for that, we need to evaluate the second derivative. So second derivative, we know it will be d dx of dy dx, right? Which is nothing but d dt of dy dx over dx dt. This is basic formulas from Calc 1. I hope you can relate to this. And recall that for concavity, if the second derivative is bigger than 0, then curve is concave up. This is also coming from the Calc 1, and the curve looks like this. If the second derivative is less than 0, then the curve is concave down, more or less like this. And when the second derivative vanishes, this will be having inflection points, okay? Or it might be undefined. Okay, this is sort of standard inflection points look like. Okay, next is a definition. When a curve is called smooth on I, where I is like an interval, if both the derivatives are continuous and not simultaneously 0 at any point of I, the endpoints are excluded, obviously. Okay, now some examples uh, to understand the concept of differentiability on parametric curves. So for this curve, x equal to cosine t and y is equal to sine 2t, t varying from 0 to 2 pi, I have to find where the tangent are horizontal, where the tangent are vertical, and I have to find the equation of the tangent at this particular point. Okay. So if I draw the curve will look like this. You can use some software to visualize, or you can try to evaluate as well by taking different values of t and guessing how the curve will look like. I'll not do that here explicitly, but you will get this as your graph of the parametric equation. So for the first thing that we need to do to see where the tangents are horizontal or vertical, we have to get the expression dy dx. And this is the formula that I mentioned, chain rule. And if I evaluate that, I'll get this quantity. Now for tangent horizontal, if I go back, I have to have dy dt to be 0 and dx dt to be non-zero simultaneously. Okay. So I have to have dy dt to be 0. That means 2 cosine 2t should be 0, right? And t is in between 0 to 2 pi. Okay. That means 2t is in between 0 to 4 pi. Okay. So 2t can be pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2, right? So therefore t can be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. These are the possibilities for t. And if you carefully draw those, you will get that this is for t equal to pi over 4. I'll get this point actually. So therefore at this point I can see that tangent should be horizontal. This point I'll get from t equal to 5 pi over 4, and here also the tangent is horizontal. This is due to t equal to 3 pi over 4. Here also the tangent is horizontal, and this is for t equal to 7 pi over 4. And you can see here also the tangent is horizontal. Okay. So so I can see that at t equal to pi over 4, my xy, this point will be cosine pi over 4 sine pi over 4, right? Which is just square root 2 over 2 comma 1. And similarly, I can evaluate all those x, y's for different values of t. I mean, this 4 values of t. And I'll get, I can continue doing this, and I'll get at the end 4 points which are of this form. Okay, cool. For vertical tangent, I remember that I need to have dx dt to be 0. Right, and dx dt, if you remember, that is nothing but minus sine t to be 0. T is in between 0 to 2 pi. When my sine t is 0, in this restriction of t, I'll get t to be 0, pi, and 2 pi. And if you try to, engage with the graph, then you'll get at t equal to 0 and pi, I'll get this point. So there you can see the tangent is vertical. And this point is due to t equal to pi, and here also the tangent is vertical. Okay, sweet. And I mean, and you also can get the value for x, y depending upon these 3 points. Those will be of this form: 1, 0, minus 1, 0, and 1, 1, 0 again. Because at t equal to 0 and pi, I'll get the same point. So these are like 2 points only. The next part was to find the tangent equation of the tangent at this point. Okay, so now my x is square root 3 over 2 and y is square root 3 over 2 as well. So if I remember, my equation was given as x to be cosine theta, cosine t, and y to be sine 2t. So therefore, I should have cosine t to be square root 3 over 2 and sine 2t to be square root 3 over 2. I should get a t for which both of these equations simultaneously satisfy. So if you carefully look, you will get t is equal to pi over 6 out of this. Okay. only t equal to pi over 6, where t in between 0 to 2 pi will satisfy both of these equation. Okay, so I get that my t should be pi over 6, but at t to be pi over 6, my dy over dx will be just 2 cosine pi over 3 over uh, minus sine pi over 6. Okay, using the calculator, you'll get this value to be minus 2. So therefore, the equation of the tangent, I know how the equation of the tangent look like. So using that formula, I'll get, this equation. So this is the tangent at square root 3 over 2 and square root 3 over 2. So therefore, basically, if I draw it, I'll get this. Okay. Yeah, so for maybe this is the last example. So for this example, I have to find the singularities of this parametric curve and determine the concavity of the curve. Remember, for the singularities, I need to evaluate dy dx. Okay, so by chain rule, dy dx is dy dt over dx dt, which is just sine t over 1 minus cosine t. Okay, so singularities will be when both of this numerator and denominator will be 0. That's what I have written there. And then from this, I'll get t to be 0, 2 pi, 4 pi, 6 pi, and so on. Only on these points, both of these two equations will be equal to 0. Now the question is, I have to find the concavity of the curve. So for that, I had to do the second derivative, okay? And I have written the formula for second derivative, which will be like this. Okay, here I have used this formula. Let me show you the formula once again. Yeah, I have used this one, this expression. Okay, cool. So now, so again, if I write down the information that I have, like if I again do the derivative of this by like UV rule, I'll get this expression, which is not pretty hard by now. Okay, this calculations, you should also verify that if there is any mistake or not. So the ultimate expression will be minus 1 over 1 minus cosine t squared. Okay, and this is always 0, right? Because I have a square term on the bottom and minus 1 on the top. So therefore, always less than 0 whenever defined. So I can say that the curve is always concave downward between the singularities, which is like except these points. So I know that at t equal to 0, 2 pi and 4 pi and so on, this denominator will be 0. So the expression second derivative will be undefined. So except at those points, this all of this all of the other points will be like concave downwards. Okay. So what I mean by that is like the curve sort of look like this, say 0, 2 pi, 4 pi, and so on. So very roughly speaking, the curves are uh, like this, probably, right? This is concave downwards, right? Or rather, the way. Let me check how the concave downwards actually look like. Maybe here. Yeah, concave downwards, like the inverse. So yeah, so the concave, it will be like concave downward in between the singularities like this. Okay, this is like very roughly speaking. Okay, so this is all that we we need for the homework 7. If you have any questions or concern, you can mail me. And for the cycloid, I guess, I will try to attach a link with the announcement or like in the module for you to better understand it. Okay, thank you.